data encapsulation. Each layer in the IPS is built on the one below. And each layer is able to encapsulate the data from the layer above, so it can move between the layers here. So data transmitted by each layer is called protocol data unit. As you can see here in this, here bidirectional, directional, and not directional. So we have headers, footers, and addresses. So the PDU, protocol data unit, in each layer contains the payload data that is being transmitted. So its common prefix, header, which contains, as you can see here, Ethernet header, IP header, TCP header here. And for the payload, this header contains information required for the payload data to be transmitted, such as the addresses of the source and destination nodes on the network. Here, source address, destination address, source address, destination address, source port, destination port. So actually, sometimes a PDU also has a footer that is suffixed to the payload data and contains values needed to ensure correct transmission, such as error checking information. This figure here, as you can see here, shows the PDUs are laid out in the IPS. So as you can see here, the TCP header contains a source and destination port number here. Source port, destination port, as you can see here, source port and destination port. So these ports allow a single node that have multiple unique network connections. So port numbers in TCP here, let me mention here. So this means tip here, port numbers. Here actually port numbers in TCP, these port numbers actually port numbers in TCP or UDP starts from 0 to 65,535 here. So most port numbers are assigned as needed to new connections, but some numbers have been given special assignments. So for example, port number 80 is for HTTP protocol, and 21 for FTP protocol, and more. So you can find a current list assigned port numbers in the ATC services file on most Unix-like operating system. So a TCP payload and header are commonly called a segment, whereas a UDP payload and header are commonly called datagram. So the IP protocol uses a source and destination address here, as you can see here, IP port, source address, and destination address. So the destination address allows the data to be sent to a specific node on the network. So the source address allows the receiver of the data to know which node sent the data and allows the receiver to reply to the sender. So IPv4 uses 32-bit addresses. Here, let's mention this also here. Actually, yes, IP version 4. Oops. IP version 4 uses 64 actually not 64, 32-bit 32-bit addresses. Which you will typically see written the number separated by dots. For example, here 1132, 168, 0.1. So these are the 32-bit addresses. So and separated by dots, as you can see here. But IP, for example, but IPv4 here, it's good to mention the tips here. It's useful. IPv, actually not IPv4, IP version 6, IP version 6 uses actually 128-bit addresses. 128-bit addresses. So because 32-bit addresses aren't sufficient for the number of nodes on a modern network. So for example here for example FE80 000 for example, and like that. So IPv6 addresses are usually written as hexadecimal numbers separated by dots, such as this. Separated by colons, actually not dots, as you can see here. IPv6 is separated by colons, but IPv4 is separated by dots. So these here writes with hexadecimal numbers, for example, AB 891 2 here, like that. So long strings of 4 times 0 numbers are collapsed into 2 columns. For example, this here, this 40 can written like just that. So this is the same as previously. So Ethernet also contains source and destination addresses. For example, here, source and destination addresses in Ethernet here. Source and destination addresses. So this Ethernet uses 64-bit value called media access control here. Ethernet uses 64-bit actually it's 64-bit, right? Yes, it's 64-bit MAC addresses which called addresses called MAC. What does MAC mean? This MAC mean is media access control. Media access control. So, which is typically set during manufacture of the Ethernet adapter. You will usually see MAC addresses written as a series of hexadecimal numbers. For example, actually like that here. 0A, for example, 00, 27, 90, AB, or F0, like that. So the Ethernet payload including the header and footer is commonly referred as frame. Here, as you can see here. Here, oops, that. As you can see here, we write it and I created an illustration here. Data transmission. Let's briefly look at how data is transferred from one node to another using the IPS data encapsulation. So now I want to create another illustration live here for better understanding. So let's computer here. Actually, it's okay. Personal computer here. This is our first personal computer. We have the switch here. Actually, switch here, and actually not switch. Let's make it more realistic. Okay, let's put it here. Rather consider this as a switch, and let's add here another computer. Actually, let's copy it. Okay, here, and let's add actually. Let's add another. For example, let's add laptop here. Here. And this is our laptop. So let's give an IP address and a MAC address to these machines here. So for example, let's make it here. Oops. This is let's make it 192 point 192.168 point for example 1.100 here, make it with a bold here, and let's make this here not 100 because they are the same network. We will make it 101 here, and let's give an MAC address to it here. Oops, MAC address, MAC here. MAC address will be 110022A2, for example, B3 and 55, and this is the IP version for address here. This is MAC. This is an IP version for address, and let's assign it. So we will not assign this MAC address yet, and let's add another here, IP version 4, make it a little higher here, and change this to for example 50 here, 50, and let's give MAC address to it, just different MAC address here, because MAC addresses are unique, but you can change MAC addresses not only your hardware but software way. So for example 667788 AB CD 33 here, for example. This is the MAC address and this is the IPv4 address of our computers. So what this will here, so now we will create actually connections on it here. Oops, let's copy and drag here. So actually let's connect this to this, and let's make it a little lower. Connect this computer to this and this to this. So in this example, the node here, this is the node here, with the IP address 192.186.1.101 wants to send data using the IP protocol to the node at this computer. With the IP address 192.186.1.50. So the switch device, this forwards Ethernet frames between all nodes on the network. So the switch doesn't need an IP address because it operates only at the link layer. In this case, actually, this is not a switch really. Switch is switch here. Switch is this. It's no router, it's router switch. This is the switch. Here. So here's what takes place to send data between the two nodes. So the operating system network at stack mode here encapsulates the application and transports layer data and builds an IP packet with the source address of 100, actually 100 source address of 192.168.1.101 and the destination address of 168.1.50. So the operating system can at this point encapsulate the IP data as an Ethernet frame. So but it might not know the MAC address of the target node, so it can request a MAC address for a particular IP address using the Address Resolution Protocol, ERP. Here, let's mention it here. ARP is Address Resolution Protocol. Here. So, which sends a request to all nodes on the network to find MAC address for the destination IP address. And then once the node at this receives are actually not this once the node this computer receives our ARP response, it can build the frame. So this will set the source address to the local MAC address of this 11.0022A2B3 and 50 So this will this source address. So this will assign it to the destination address. So 6677888ABCD33. And the new frame is transmitted on the network and is received by switch. And finally, the switch forwards the frame to the destination node, which unpacks the IP packet and verifies that the destination IP address matches. So then the IP payload data is extracted and passes up the stack to be received by the waiting application. In this lecture, you will learn the network routing here. Let me actually increase the size a little bit. Just not. Okay, so Ethernet requires that all nodes to be directly connected to the same local network. This requirement is a major limitation for a truly global network because it's not practical to physically connect every node to every other node. So rather than require that all nodes to be directly connected, the source and destination addresses allow data to be routed over different networks until the data reaches the desired destination node, as shown in this figure here. So in this figure I created one. This shows the Ethernet networks, each with separate IP network address ranges. So as you can see here, the operating system network stack node here encapsulates the application and transport layer data, and it builds an IP packet with the source address of 192.1.1.101. And the destination address here, as you can see here, 100, actually not 100, this is the 200 because this is the absolutely different range, 200.150. So then the network stack needs to send an Ethernet frame, but because the destination IP address doesn't exist on any Ethernet network that the node is connected to, the network stack consults its operating system. operating system routing table actually. So it will look routing table. So in this example, the routing table contains an entry for IP address 200.0.1.50. So the entry indicates to the router on IP address 192.1.1.1 to this knows how to get to that destination address. So actually, in this case, in our case, this router here knows where to go with that address. And then completed, and the new stage comes. This is the third stage. So then the operating system uses ARP, as in previous lecture we write something here. What ARP means? ARP is address resolution protocol. Actually, this is the ARP is address resolution protocol. So then the operating system uses address resolution protocol to look up to the router's MAC address at 192.1.1.1, and the original IP packet is encapsulated within the Ethernet frame with that MAC address here. So, and then router receives the Ethernet frame and unpacks the IP packet. Here, when the router checks the destination IP address, it determines that the IP packet is not destined for the router, but for a different node on another connected network. In this case, the router looks up the MAC address of this device, 200.0.1.50, and encapsulates the original IP packet into the new Ethernet frame and sends it onto the network 2. This is the network 2 and this is the network 1. Network 1 here and network 2 here. So, and lastly, the destination node receives the Ethernet frame and unpacks the IP packet and processes its contents. So the routing process might be repeated multiple times. For example, if the router was not directly connected to the network containing the node of 200.0.1.50, it will consult its own routing table and determine the next router it could send the IP packet to. So clearly, it will be impractical for every node on the network to know how to get every other node on the internet. If there is no explicit routing entry for the destination, the operating system provides a default routing table entry called the default gateway, which contains the IP address of a router that can forward IP packets to their destination.